Hi there everyone, today we're going to look at an exponential growth and decay. Got a new topic for a GCSE for this current syllabus, but it's obviously something you need to be aware of. So we're going to go through it. We're talking about what it's all about. You might come across it in science, might come across other subjects, but of course the idea of crossing over other subjects with maths is quite important these days when looking at problem solving, so the idea of putting things into context is absolutely critical. All right, so let's have a look anyway. So exponential growth, something that occurs naturally. So it would not be surprised me if we're talking about something from a nature perspective, but of course it can appear in other areas of life. But it's where the rate of increase changes. It becomes faster and faster and faster. All right. So currently, when we're talking about the coronavirus in the news, and depending on when you're listening to this, the idea of thinking about how quickly that is kind of growing, and any other kind of virus growing, obviously. It tends to be exponentially. It starts off relatively small and grows and grows and grows and grows very, very quick. All right, so it's something to be wary of. All right, so growth of bacteria and disease, they can tend to take that. Human population did, for some time grow exponentially. However, these days it tends to be kind of tapered off. But ultimately, it used to be a case of it just grow and grow and grow and grow and grow, and that still happens in the wild occasionally. Compound interest, it's slow exponential growth, but it's exponential. If you think about your bank account, you think about those people who have millions, the more money you have in the bank, the more money you get. All right, the less money you have in the bank, the less money you get. So it grows increasingly faster as the more money you've kind of got in there. All right, so an exponential growth takes a certain format. Okay, it's y is equal to some value times a to the x. All right, so that k tends to be a kind of constant. Normally your starting value, and then it's grown and grow exponentially based on some kind of multiple. All right, so for example, if I had £1,000 in a bank, my k would be 1,000, and then I would times it by some number, and then would leave it for how many years I would leave it in there. So a would be the interest rate I would get, and then the power of x, so would that be the number of years I would left in there. And obviously if I put those number in, so let's say I had £1,000, an interest rate of 2%, so times by 1.02, and I left it for 20 years, and then x will be 20. Then using the compound interest rule, and if you're not quite sure how to work out compound interest, then that's what compound interest does. Then that would give me how much money I would expect after 20 years. All right, so that's what that's all about. So just in summary, so k represents the initial point in time, an initial value effectively. So again, using my example, it's £1,000 in the bank. X tends to represent time, because we're talking about exponential growth or something to that effect, and it tends to be over a period of time. All right, so that's given a variable, and then a, which I've not mentioned, well, that depends on how quickly it grows. All right, so for compound interest, it was going to be relatively small in terms of that variable, like 1.02, for example, or 1.03. Whereas growth of bacteria, well, that might double every 2 days. So that means a might just be 2. So it really depends on what the criteria is. So you need to know what that is in terms of calculating it. So that's exponential growth. So y equals ka to the x. It always takes that kind of format. And the graph, if I was going to draw a graph, as you probably would expect, it would look something like that. It kind of curve up and up and up and up and up, and obviously you just keep getting bigger and bigger and bigger as you progress. And as you think about the powers, well, if I concentrate on this value here, well, that number there is going to be your starting point. All right, because anything to the power 0, so this is indices, is 1. So that to the power 0, no matter what a is going to give me 1 times by k. So that's going to give me my starting value. And then as I go to the power 2, 3, 4, 5, 6, 7, and so on, as long as that's bigger than 1, then it's going to keep growing and growing and growing and growing and growing, hence it going up. All right. Now, if we are talking time, then this is probably not relevant, because it's only going to start here and kind of move upwards. We're not really going to have negative time, but it might be in relation to the graph that you need to understand. It might not be time, it might be something else. All right, so potentially negative. All right. The other one to look at is decay, which is kind of the inverse of growth. That means it's going to go smaller, 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 and the rate decreases again, will kind of change. It'll get less and less and less and less and less. All right. So rather than getting bigger and bigger and bigger and bigger, it will get smaller and smaller and smaller and smaller. But the rate will kind of get less and less and less. You'll see what I mean in a second when we look at the graph. So good examples in terms of this one. Radioactivity, not radioactivity, radioactivity. All right, check the spelling on that one. Radioactivity. Depreciation. So the idea of a value of a car would depreciate, and it'd probably get to a point where it kind of tails off. So it might start off worth £40,000, £30,000, and then eventually, no matter how old it gets, it might end up being always £10,000. All right, it might tail off. Now that's not an exact science, because some obviously cars become classic cars, and therefore the value goes back up again. So it's not necessarily exactly perfect. All right, but a little bit like the last one. It's the same kind of format in terms of its equation. It's y equals ka, but this time it's minus x, ka to the minus x, and that means it's getting smaller and smaller and smaller. All right, so your graph would tend to look like that. So you can see it starts off from the left hand side at a certain height and get lower and 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 so on and so on. So it kind of tails off. All right, it's like a reflection in the y-axis. All right, and if you've done graph transformations, you'll understand that because that means a minus x, then what's happened is it's reflected in the y-axis, which is why it's gone like that. But ultimately, yeah, decay tends to go like that, and like I say, so it kind of tails off to a certain point. Same as before, is that when it crosses the x-axis here, sorry, the y-axis, I should say, when it crosses the y-axis there, that'll have a value of 1, or whatever a is, I should probably say, because it's going to be so whatever k is, I should say whatever k is, because anything to the power 0 is 1. All right, so if x is 0, a to the power 0 is 1 times by k. So that value that crosses there will be k. All right, but there is another lesson on this when I talk about using this in kind of context. All right, so that's exponential growth and decay. It generally gives you an idea in terms of the graphs and the equations, but obviously the application of it is come wider and fairer field. So what you need to learn is these equations and know how to put them into a graph. And I suggest you probably look at one of my other lessons, which is solving exponential graphs, which is again part of everything that's on maths-school.co.uk. So look at the link at the bottom, go onto the website, access the other resources, and have a go at some of the quizzes that are on there. Okay, thanks for listening.